Welcome back to another lecture on differential equations, more specifically ordinary differential equations. These past couple lectures, we talked about solving ODEs using the characteristic equation and then using the method of undetermined coefficients for non-homogeneous systems. And so now we're still going to use those two methods. However, we're going to be discussing about a different type of ODE and using what this method is known as the Cauchy Euler method. So let's get started. Before we discuss about the Cauchy Euler method, I did mention that we will be discussing a different type of ODE. And so the Cauchy Euler method is used to solve an ODE in the form of ax squared y double prime of x plus bx times y prime of x plus c times y of x is equal to g of x. And so this equation is famously known as the Cauchy-Euler equation, hence the Cauchy-Euler method. And it appears in a lot of physics and spherical coordinates. And so this, if you kind of look at it and squint your eyes a little bit, tilt your head a little bit to the right, this kind of looks like an ODE with constant coefficients. The only thing is that we have an x squared and x in the equation, so we need to find a way to get rid of the x and x squared. And so what that means is if we're able to get rid of those x's, then we can use the characteristic equation or the method of undetermined coefficients, because converting the equation to the ODE with constant coefficients allows us to use it. And how do we convert this equation to become an ODE with constant coefficients? Well, you get rid of the x and the x squared. So how do we do that? When it comes to solving ODEs, a lot of it comes with guessing. And so what I'm guessing is the way this was kind of solved is just pretty much guessing, and in this case they used a method known as a change of variables. And so what this change of variable is they allowed a new variable that we're going to call t, and we're going to let that equal to natural log of x. With this change of variable, we can have a function that we'll call f of t, which we can substitute t to being f of natural log of x, and we can let that equal to y of x. And so if we let y of x equal to f of t, which is f of natural log of t, then we can take the derivative of y of x, leaving us with y prime equaling to f prime of t times 1 over x, because it's using the chain rule. And then y double prime will be f double prime of t times 1 over x times 1 over x minus 1 over x squared times f prime of t. So this one's using the product rule and the chain rule. And so if you simplify that a little bit further, you can have 1 over x squared times f of double prime of t minus 1 over x squared times f prime of t. And so now that we have this, the derivatives, we can now substitute this back into the original ODE. And because the ODE has y of x, we already found what y of x is and its derivatives. So when we substitute that in and do a little bit of simplification, we will get the ODE, the new ODE, being a times f double prime of t plus b minus a, and that quantity multiplied by f prime of t, plus c times f of t, and that's equal to g of x. Now obviously we can convert g of x to be some function with respect to t, but more on that later. This new equation that we have is what is known as an ODE with constant coefficients. So we can use the method of characteristics or method of undetermined coefficients to solve this problem. So we're going to start off with the method of characteristics because that one's more simpler. And so with the method of characteristics, that means that this equation must be homogeneous, meaning that our g of x or g of t or whatever variable with respect to t is going to be equal to 0. And so when we let that equal to 0, then we can find our solution for f of t using the characteristic equation, meaning that we have to let f of t equal to e raised to the rt, thus giving us the characteristic equation ar squared plus b minus ar plus c, and then times the function f of t. And so when you find your roots, you find your solution, as I mentioned in the in the homogeneous equation with constant coefficients. And so when r1 and r2 are real numbers, then we get the solution f of t is equal to c1 e to the r1 of t plus c2 e to the r2 of t. This is nothing new. However, this is not our solution. We are looking for a solution of y of x. So y of x, we know what that's equal to. We know that y of x is equal to f of t, and f of t is the same, and t is equal to natural log of x. So what we can do now is we can substitute t with natural log of x, giving us our function of y of x as well. And so our solution of the function y with respect to x would be c1 e to the r1 times natural log of x plus c2 times e raised to the r2 times natural log of x. Now, if you remember back in algebra, you know the identity that e raised to the natural log of x is just x, and what you also know with logarithmics is that any constant multiplied by natural log of x is the same thing as natural log of x raised to that constant, or natural log of x raised to that constant. So we're going to use those two properties, thus giving us c1 is equaling to natural log of x raised to the r1 times times c2 times e raised to the natural log of x raised to the r2. And then we're going to use the property of e to the natural log of x is equal to x, thus canceling out the e and the natural log of x, giving us c1 times x to the r1 plus c2 times x to the r2. And that will be our solution to the original ODE. And so now what this gives us is the true solution, or I guess the general solution. And so what that means is the other two cases, when r1 and r2 are the same, then our solution f of t will be the same thing as we usually see it. But when we convert it back to the original solution, y of x, we're going to get c1 x to the r plus c2 times x to the r times natural log of x. Now, why is that natural log of x there? Well, it's simply because if you like I mentioned in the repeated solution with homogeneous equations, we had to multiply the second solution by x. But we also know that, well, in this case it would be t, and that's a typo. It's supposed to be c2 of t e to the r2 of t. But we know that we did the substitution that t is equal to natural log of x. So that means that our t, which is x by accident, is actually natural log of x. And then for the case that r is a complex conjugate, then it will pretty much be the same thing. F of t will be the same solution that we've seen in the past, but the original solution, or the more general and specific exact solution, will be c1 x to the a times cosine b natural log of x plus c2 x to the a times sine b natural log of x. So that pretty much covers the case where we use, or when our function is homogeneous. In the case that g of x is equal to capital G of t, and that's not equal to 0, which means it's non-homogeneous, then the method of undetermined coefficients can be used, which is something that we know how to do. It's just, it kind of varies case by case, but we will do more examples on those. But yeah, that's pretty much it for this lecture, and I'll see you guys in the blackboard so we can do a couple of examples with both the homogeneous and non-homogeneous case.